Okay, welcome back to a new physics tutorial. In this video I would like to cover one topic which is also usually part of examinations, especially in case of quantum mechanics, and this is the very typical one-dimensional infinite potential well problem, which means basically a particle in a box. Yeah? So we have an electron which is trapped inside an infinite potential well with a length of 0.1 nanometer. And we want to find now a formula for calculating the energy levels of this electron inside this box. And we want to write down the wave functions, that describe the waves of the electron inside this potential well. And we will go through this step by step, and I hope that after that you are not only understanding how this exercise can be solved, but also you can use this solution for similar exercises where you don't have an infinite potential well, for example. Okay, so the first thing which you will do, as usual, is making a sketch. So I will try to draw this as good as possible, and this is the potential well. Later we will also insert the wave functions here, so I will try to make it a little bit bigger. And then we have, if nothing else is mentioned in the exercise, it means the potential inside the well is 0, and outside in here and here it has to be infinity. So the electron cannot leave this this box. It's really trapped inside. It can be reflected from one side to the other and moves always around, but it cannot leave this box. And this is very important in order to really calculate the energy levels later. Okay, so the next thing which we need is defining the direction of our x-axis, and this can be, for example, done in this direction. And we can say here x should be equal to 0. And here x should be equal to a, because the length, as I said before, of this potential well is 0.1 nanometer. So here in this case, this would be equal to our value a. And now the first thing which we can do, we have to write down the Schrödinger equation. So I don't want to write down the full one, because this is a little bit maybe too complicated. But we know already that we have a one-dimensional problem. And we know that that we have a zero potential here inside this potential well. We don't have a time dependency. So in this case, we can use actually the time independent one-dimensional Schrödinger equation without any potential. And this can be written down very simple by just minus h bar square divided by 2m times d square over dx square psi of x, and this has to be equal e psi of x. So this is only true for this certain example here, as I said, but if you have a potential inside this well, then you would also have to add the term here plus v psi and so on. And if you have a time dependency, this would be actually the wave function would also depend not only on x but also on t. And for three-dimensional case, you would have to insert the Laplace operator here instead of the just derivative of d over dx second order. So what we have now is a second order differential equation, and this we have to solve. And you can do this in several ways. For example, if you know that some sine and cosine functions can solve that, you could use this. But this is maybe only true for a specific case, like in this case. So a more general one, or the most general ansatz which you can use for a differential equation with second order is the following. So we write here ansatz, and then we can note down the function which could solve that, which is psi of x equals any arbitrary constant times e to the power minus ikx plus b e to the power minus, there's no minus then in this case, plus e kx. E to the power ikx, and this means that we have here exponential function, we have the Euler number, we have here an imaginary unit. So you find, if you take a look at some math books, you find out that this is exactly the equation that solves this, the most general one that you can find. And now the only thing which we have to insert, the only thing which we have to do is now inserting this ansatz into the Schrödinger equation. Yeah, and this we can do now. And when we do this, we get here, I will maybe write it down one time complete, how it looks like. Minus h bar square divided by 2m, d square over dx square of a times e to the power minus akx plus b times e to the power ikx. And this is equal, as I said, e times a times times e to the power ikx, and here should be a minus, plus b e times ikx. Okay, we have not done anything else except just inserting this into our equation. Okay, and now we can really calculate something, and this is here this second order derivative. And yeah, because we have here our Euler number and we have an exponential function, we can just take out these constants and place them in front, which means that this minus here actually vanishes because of this I, the product of i's. And yeah, this k gives a k square. Yeah, so what we can write now here is h bar square k square divided by 2m, and then we can insert the same function here, minus akx plus b e ikx equal e times a e to the power minus akx plus b e to the power ikx. Okay, this is in principle very simple, but you see now that on both sides we have the same term, which is in this brackets here, in this parenthesis, so we can remove that, and at the end the final formula remains, which is h bar square k square divided by 2m, and this is E. Yeah, so now we have a relation between the energy and k, which is this constant here. But of course we don't know k at the moment, so we have to find out from where it comes and how we can calculate that in order to really calculate E. And this we will do with another method in case of differential equations, which is called boundary condition. So we have to define our boundary conditions now. And for that we have two, as you will see now in a few seconds. So we will start with the first one. And here in this case we can write psi of 0. So x equal to 0, which means that we are here on this side, and there the wave function has to vanish. Yeah, the electron can just not be there because it cannot pass this this well to the outside. So in this case we can say that our boundary condition is psi of 0 has to be 0. And now I will make a new page, so it will be a little bit easier for writing. So now this means that when we insert the value 0 into our wave function that we have defined before, then we can write here IE minus AK 0 plus B E to the power plus IK 0, and this has to be equal to 0, as I said. And this means that, of course, e to the power 0 has to be 1. So this is actually 1, and this is actually 1. And this means that at the end, e plus b has to be equal to 0. And this means a has to be equal minus b. Okay, and now we can define our second boundary condition. And this means that psi of a, which is the same here on this side, the same condition has to be applied, and this means psi of a has to be 0. And this means that now a times e to the power minus ika plus b e to the power ika has to be 0. And now we can actually use a trick here. Yeah? So calculating or doing some calculations with this E function is a little bit tricky, yeah. But we know that there is a relation between these E functions here and the sine function, the trigonometric functions actually. So now we can use the following formula, which says that sine of x can be expressed by 1 over 2i times e to the power ix minus e to the power e to the power minus ix. Yeah, and then we can insert that, and this means that here a over 2i sine, and then we have to replace that, k times a has to be 0. And the condition that we can derive from this is, of course, when is sine of some variable is equal to 0. If there's a constant k included, only if this constant k is n times pi divided by a. And this you can easily prove yourself. So now we have a condition for k. This is actually any integer number, positive integer number n times pi divided by a. And this we can now insert into our wave function. Now we can insert this into E, not into our wave function, into our energy formula that we have derived before, which was here. And this then finally leads to E equals, I can just note it down one time more, as we have derived it before. And when we replace k, then we get h bar square, this I will write maybe a little bit different, h bar square pi divided by 2m a square n square. And now we can also replace h bar with h over 2 pi. And and because we have h bar square here, we can write h square divided by 8ma times n square. Yeah, and because the energy depends on the energy level on n, we can write here now n. Yeah. So now we have different energy levels. So depending whether we have n equal to 1, n equal to 2, n equal to 3, and so on, we get different energies of the electron. Yeah. Later I will show how it looks like for the electron, but now we can maybe just calculate some values to prove that this works. So I just did it one time, and I found out that when we type in the values, the Planck constant, the electron mass, the length of the potential well, and also the n equal to 1, yeah, then we get as a result 37.1 electron volt. You can also do this once yourself and check whether it's correct. The same I have done for E2, and here I got 150.4 electron volt, just because n, all the constants are remaining the same, but of course n changes from 1, 2, 3 and so on. So we get actually a square dependency between the state and also the energy level. Yeah, and the same you can also do for E3, E4 and so on. But now it means that part A is finished because we have now our energy formula. So now coming to part B, where we actually want to derive our wave function of the electron. And this we can, we have it already, the wave function in principle. Yeah? We have defined that here. So maybe I can write it one time more down. So this 2i we can actually put into our constant a, because it's also more or less a constant. In this case, a complex constant, you can say. So we can just write our wave function as psi of x equals a times sine n pi over a times x. This is our wave function, and we have to determine now the constant a. This is very important. We have to find a value for that, because now at the moment we have some arbitrary wave function. And in order to do that, we use a concept which is called normalization. And this is a very common concept in case of quantum mechanics. This is used to determine some arbitrary amplitude. And in order to do that, we know that the overall probability of of a wave must be 1, yeah, over the whole volume. And in this case, then we can write, so the probability of a wave function is proportional to the integral of psi, and then we have to use the complex conjugated form of the wave function times psi, and then we can integrate in general from minus infinity to plus infinity, and of course over dx if we just use the one-dimensional case. Yeah. So now we can insert our wave function actually. For the constant which we have defined, this is actually a square. Yeah. So we can just take this out. And now we have to integrate. Minus infinity to infinity would be a stupidity in this case, because we only have to integrate from within our potential well from 0 to a. And then we have to insert our sine square from our wave function, n pi divided by a x dx. And this integral now we have to actually solve. And I have done this already, so you can find out that, or you can just look up the integral of sine square x in a database, or you can also use a computer algebra system to do that, or you can do it yourself with partial integration. But I will tell you now what comes out. So what we can use here is the relation integral sine square x equals x half minus sine 2x divided by 4 plus an integration constant c. Yeah, so now we can use this equation in order to write, in order to solve that, which means now in this case the integral from minus infinity to infinity of psi star psi dx is given as x half from this formula above minus, because of chain rule, a divided by 4n pi sine 2n pi over a x and integrated from 0 to a. And now we can make another page. And this is then given as a square. When you insert all the limits, basically, you get a over 2 minus a divided by 4n pi sine 2n pi. Yeah, this is everything. And now you can see we have here n times pi, and of course sine of any integer value times pi must be 0. So this cancels actually out. And now what remains is a square, a half, and this, as I said, should be equal to 1. And from that then we can calculate our constant, which is given as a equal the square root of 2 divided by a. Yeah, and now the only thing which we have to do, we have to insert into the wave function. And this gives then psi of x equal square root 2 divided by a sine n pi over a x. Yeah, and this is then the result of our wave function. So this is actually here how the wave function looks like. We can also write here psi n, because it depends here mainly on the state, on n. And also what we have derived before is the formula for the energy values, which is given actually here. Yeah. So now you can calculate both the energy levels and the wave function, and now we also want to draw that finally here into our potential well, as I said. So when you really calculate the values of that wave function, then you find out that for the state n equal to 1, you get something like that. You have here the nodes on both sides where the electron is reflected and the wave function is 0, and the maximum elongation you have here in the center. And this is the case n equal 1. And for n equal 2, this would look like that you have an additional node here in the center, and then the wave, when you calculate really this sine function, then it would look like that. Yeah, and the same you can also do here. Then with n equal to 3, you will get 2 nodes in the center, and 3, 4, and so on. And so your wave function actually changes according to the state. Yeah? And then for each of these wave functions, you can then also define the energy, which is E1, which is E2 in this case, and so on. And yeah, so the shorter the wavelength here, as you can see, the higher the energy level, of course. Yeah, because according to quantum mechanics, a shorter wavelength means a higher frequency, and this means actually a higher energy. So yeah, this can be done very simple, as you saw. You can use the same method to also calculate the energy levels in a hydrogen atom, for example. The problem is there the potential is not zero. You have a Coulomb potential, which goes down with 1 over r square. And then you cannot use this simple Schrödinger equation here for a zero potential. And for more complex situations, maybe you can even not use the one-dimensional. I mean, for a hydrogen atom, you can also not use the one-dimensional Schrödinger equation anymore. Because you have to do it in with spherical coordinates. You have to solve it in principle because you have a spherical symmetry. And yeah, and the more deeper you go into quantum mechanics, the more complicated the Schrödinger equation will be, the more complicated the ansatz will be. But the general idea behind it is always the same. Yeah, you have to write down your Schrödinger equation, you have to make an ansatz which solves this Schrödinger equation, and then at the end you have to insert your boundary conditions, and then you get the so-called energy eigenvalues, which are shown here on the right side, and also you get automatically the wave function from that. So you can try this, and yeah, hopefully you enjoyed the video. Hopefully you learned something regarding how to solve Schrödinger equation in certain circumstances. And if you liked the video, please hit the like button. Please subscribe my channel if you have not done so far, and if you don't want to miss any further tutorials. And hopefully see you soon for a next video.